السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, today the plan is to give you a very brief introduction to the transformer architecture and BERT. The reason why we are doing that is because BERT had made a big breakthrough in several natural language processing tasks, but more specifically in IR. So we'll have to give this introduction, and then inshallah in the second half of the lecture we will talk about how we can use BERT in IR or in ranking in particular. So we'll start with the transformer. So what is the transformer? The transformer is a neural architecture that was designed to solve sequence-to-sequence tasks. What do you mean by sequence-to-sequence tasks? I have a sequence of items in general, and I want to produce a sequence of other items. So for example, machine translation problem is considered to be a sequence-to-sequence task. I give a sequence of words in one language, and I want the machine to give me back as an output sequence of words in the other language. So for example, if I have this, je suis étudiant, I think in French, the output will be I am a student in English. So this is an example of sequence-to-sequence tasks, and there are many sequence-to-sequence tasks, and the transformer was designed for such tasks. So what is exactly the design or the architecture of the transformer? If we look into that black box, we'll see that we have two sides. We have what we call stack of encoders. So this is a stack of layers. We call them also blocks of encoders. And we have also a stack of decoders. The stack of encoders are at the input side, and the stack of decoders are at the output side. So the input goes into the encoder side. Then the encoder does some things, as we will see, some embeddings for the words, and some encodings for the words, and then these encodings are used to decode the input into the output, depending on the task that we trained the architecture on. So if we look into these stacks, we'll see, of course, layers of encoders and layers of decoders. One thing that we need to mention here is that the encoders are all of the same architecture, and decoders also are all of the same architecture. So we will not say decoder number 3, how it is different from decoder number 2. No, they are all the same exact architecture, but of course they don't share the weights or the model. Each one has its own weights, okay? But it's the same architecture, the same structure, okay? But of course, each layer or each block of these will learn something different, will have different embeddings, as we will see, okay? The link between the encoder and decoder is at the output of the last one. So as you see here, the input to the first encoder is the actual input to the transformer, and then the output of the first encoder goes into as an input to the second one, and so on. Same here, the output of the decoder is an input to the output of the first decoder is an input to the second decoder, and the output of the second decoder is the input for the third one, and so on, until we have the final output, okay? And the number of encoders is the same like the number of decoders. So that's the very high level architecture of the transformer. Let's now get into details, or a bit of details into each side. So we'll start with the encoders. Now we'll focus, since we said that the encoders have the same architecture, so we will just focus on one of them and look in more detail into each of one of them. Okay, so each encoder. Okay, so I have to just one thing. One second. Each encoder has two sub-layers. So the terminology here is that each encoder is a layer or a block, both are used, and the encoder itself has two sub-layers. One is called self-attention layer, and the other is feed-forward neural network. I think you are familiar with feed-forward neural network. This is standard neural network that has, in general, multiple layers. Here, I think in the transformer, they are just using two layers. But we don't care exactly about the number of layers within the number of neural network layer within the feed-forward neural network sublayer, but we'll just use it as a black box. Okay, but we know that this is a standard feed-forward neural network, as you learned it before in machine learning course, or I hope that you watched my video in machine learning. So this is something like this, just to give you a quick look into that. So this is something like one layer of nodes and another layer of nodes, and each one here is connected to the other. Okay, so this is what we mean by fully feed-forward neural network. Okay, so we have all of these. Okay, so we call this two layer. Actually, this is one layer, but in transformer, I think they have two layers. Okay, with different number of nodes in each layer. But we not care. We not say much more about that. So this is just the feed-forward. So we'll have everything here again. Okay, we'll just call it feed-forward neural network. Okay, so that's the top sublayer in each encoder. Now, the decoder has three sublayers, so it has the same similar sublayer, two sublayers like the encoder, but they have also a third one in between that is called encoder-decoder attention, and of course we will explain what does that exactly mean. Okay, so far we said that we have two stacks. We have a stack of encoders that will take the input, learn something out of it, and then pass it to the decoders, the stack of decoders, and the stack of decoders will use that to produce the final output. Okay, same structure at each block or at each layer. Each layer of the encoder has two sublayers, self-attention and feed-forward, and each layer of decoder has three sublayers, self-attention, encoder, decoder attention, and feed-forward. Now let's get into the encoder in more detail. So we said that we have two layers. So the input, let's say that now we are looking into the first encoder. So the first encoder will get the input to it is the actual input to the transformer. So in our case, the input is words. Okay. Of course, you know by now that words cannot be used directly into an architecture like that. So we have to encode it somehow. So we have to use embeddings for it. Okay, so that can be one-hot encoding, that can be word-to-vec, that can be glove, any type of embeddings, static embeddings that we can start with. Okay, so we'll assume that for each word here in our example, the French to English example, we have the embeddings for each word, and that will be the input to the transformer. Okay, so the transformer actually allows an input for hundreds of words. Okay, for BERT, I think it's 512. I think for the transformer, the same 512, and that's actually the number of tokens. Okay, and for each token, we can get its embedding. Okay, so that's the embedding vector. Of course, it doesn't have to be for values only, but this is just for illustration. So the input will be the input embeddings for the words. Now these words each one goes into all of them will go into a layer called self-attention. And then this self-attention layer will output an embedding for each word, for each input word. Okay, so there is an intermediate embedding here for each word. Okay, that intermediate embedding will be input to the feed-forward network, and then we will have the output of each word again from that layer. Okay, so that will be the output of encoder number 1, and that output will be an input to the next layer, to the next block of encoder. Okay, fine. Now, one thing that we need to say before we get into the self-attention layer is that the self-attention layer involves or considers all the embeddings. Okay, so there is a dependency here between all embeddings, but once we get over the self-attention, these embeddings, okay, you will see me or you will hear me saying embeddings all the time, because at each level, or at each state of the architecture, we can consider this an embedding, okay, a type of embeddings. So these embeddings, or this output, you can call it the output of the self-attention layer, will go to the next layer, but these will be in parallel, completely independent. So there is a difference between the self-attention layer and the feed-forward layer, in that the inputs here, the outputs of the self-attention layer is dependent on all inputs. But here, once we pass this sub-layer, the output for each, or the embeddings for each word, can go in parallel, completely independent from the other words, from the other embeddings. And this is very important in terms of scalability and efficiency of using the transformer. Okay, now it can scale because we can parallelize this on multiple cores or multiple machines if we need to. Okay, so this is a note about dependency. Any questions so far before we get into the self-attention layer?
Yes, Doctor.
Yes.
Do you mean by dependent that each word depend on the other? What do you mean by dependent and not dependent?
Very good. You see here Z1 and Z2? You see this, right?
Yes.
For example, Z1 is the corresponding embedding of X1 out of the self-attention.
Okay.
Now Z1, the value of the values in Z1 embeddings depends on both X1 and X2.
Okay.
Okay. Same Z2 also. Z2 depends on X1 and X2. Okay. But R1 doesn't depend on Z2. The R1 depends only on Z1, and R2 depends only on Z2. Okay.
Yes.
So there is a separation here, but there is no separation here. All of these, this is all depending on each other, but here there is independence.
Yes, I understand.
Okay. So we cannot parallelize this. We cannot parallelize this easily. Okay, but this can easily be parallelized because they are completely independent once we get Z1 and Z2. Okay, is it clear now?
Yes. So we can X1 can parallelize. You mean that Z1 and Z2 can go in parallel both to the next layer, but
exactly.
X1 and X2 it should be one after one, or what?
No. All of them are simultaneous. Okay, so there's a difference between inputting all of these simultaneously and parallelizing them. Parallelizing means that you can compute or you can use them independent from each other in parallel, so that you can save time. So you don't need to create R1, then you create R2, then you create R3. Okay, you can just parallelize these processes. Okay, do them all in parallel at the same time and save time this way. Okay, but I think a good note here is that this input, all of the words will be the input simultaneously. So this is not sequential. I don't input X1, then I input X2, then I input X3. No, this is not like recurrent neural network that we discussed briefly last time. It's not like that. This is not sequential. This is all the words are input at the same time. Okay. Any other questions? Okay, so let's move on. Now let's talk about self-attention. Now look at this sentence. The animal didn't cross the street because it was too tired. Okay, because it was too tired. Now, if I asked you, what does it in this sentence refer to? What is your answer?
Animal.
The animal, right? The animal. So it here refers to the animal, right? So this is very easy for us, right? As humans, I don't think, in one, if I asked 1,000 persons, what does it refer to? Maybe 999 will say animal. Maybe one will say street if he's still very young, not knowing the structure and the meaning of the sentence. But it is very easy for humans, right? But that's not easy for machines. That's not easy for machines. So when the model is processing the word it, self-attention layer tries to associate it with animal, tries to involve the word animal in encoding the word it. Okay, because it is related to the word animal in this sentence. Okay, so the self-attention layer, the role of the self-attention layer, or the job of the self-attention layer, is to find within the sentence for each word what are the other words that are related to it, so that when it encodes that word like it involves or it considers the encodings of those other related words. Okay, this is what we call this attention. Okay, so when we process it attends to animal. Okay, it considers the word animal when we encode the word it. And of course, that is done for each word in the sentence. Okay, so this is very important because it tries to understand how we can relate words together, okay, that appear in the same sentence. And this is actually contributing to the understanding of the entire sentence, okay? Because if I don't know what it refers to or what it means here, then I have something missing in my understanding of this sentence, right? So a good model will actually try to associate these two words together so that when I have an output for that word, remember in the when we talk about this back, each word here will have a corresponding output from the self-attention layer. So this is like an embedding. This is like an encoded version of that term. Now, with self-attention, this encoded version, Z2, should depend on the corresponding encoding, or should relate somehow to the corresponding encoding of other words that are related to that word. Okay, so let me say it. Let me show you an example here out of the trained transformer. Okay, for exactly this this sentence. Okay, so the animal didn't cross the street because it was too tired. First, one note before we talk about self-attention here. You notice that these are not all words. Okay, so the animal did, and then the apostrophe, and then T, then cross the street because it was too tired, then D. What are these? Okay, of course, we know very well from previous lectures that these are terms, or actually tokens, okay, in the terminology of transformers. Okay, so transformers have their own pre-processing that chunk the input into their own terms, but they are actually called tokens. Okay, we'll not get into that. There is a way, there are methods that do that. But anyway, these are the tokens that are actually the input to the transformer, not just the words. We just use the words in the slides just for simplicity, but they are actually tokens, and they are tokenized by specific methods. Now, the token or the term it, okay, you see here that the attention weights, because the attention, the out of the attention self-attention layer, we can get some weights that relate each word to the other words. Okay, so the strength of the lines here and the strength of the color here refers to higher weights, okay, or higher attention. So looking at it, you will see that it attends to the animal much more than the others. Of course, there are some attention to the others. That's a machine learning, okay, trying to learn these relations, but the highest weight or the highest attention is actually to the animal, which is the correct thing. Okay, so that's the role of the self-attention layer. Now, the self-attention layer does this for every word or for every token. Okay, for every token, there is like an attention vector that shows me which words are more related to that word. Okay, what is the impact of that? Now, when I provide the output from the self-attention layer or sub-layer for that word, which is the encoding at that level, at that layer of that word, it will be related to the encoding of those other words that are related to it. Okay, so let me say it in words like that. So as the model processes each word, self-attention allows to look at other positions in the input sequence for clues that can help lead to a better encoding for this word. Okay. And self-attention is one of the key concepts behind transformer, because now it allows the architecture to learn relationships between words within the same input. Okay, within the same input. So it relates these words and better understand the sentence as a whole, and better providing the embeddings for each word. Okay, we'll stop here and ask you if you have any questions, because this is one of the key important points about transformers. Any question about this? Yes.
So you mentioned that the way that we understand this self-attention is through machine learning. Is that the reason why there is no natural language processing way of trying
No,
to?
I didn't say that understanding this is by machine learning. What do you mean by that?
Sorry, I thought that's how it
So let me clarify this. Do you mean that these weights will be learned?
Yes.
Yes, of course. This will be learned automatically. This will be learned during the training phase of the transformer, using, of course, so many examples.
Yeah. So I was curious, like, why not use natural language, since
this is a way of understanding the natural language, Muhammad.
Yeah.
Okay. So we are training the architecture to understand relationships between the words.
But we're not relying on the language structure. We're just relying on essentially trial and error for machine learning, right?
No, it's not trial and error. Trial and error for the task. Okay.
Yes.
Remember that the task here is about sequence to sequence. It's a sequence to sequence task. So, for example, here machine translation. The task is machine translation. Yes, trial and error at the level of whether this sentence is a translation for that sentence or not, or whether this word should appear in the translation or not, but not at the level of the attention. The level of the attention is self-trained given the data that we will use for training this transformer. Okay, so in the label data, we don't say that it actually refers to the animal. It will learn it through the training phase. There are, of course, more details here, and I will not get into exactly how self-attention works. There are mathematical operations here that can be explained, but we'll not have time for that. We will only explain things that are the main concepts, and that will benefit us in ranking. Okay, but if you are interested in how self-attention actually works, you can see the readings. Okay, that the links to the readings that I put for that lecture, you will understand it much better.
Certainly. Then one last question is, then the underscore that we add are in the tokenization stage, right? So we're adding this,
yes, exactly,
for each word, so we identify that the word is over. There's no, as you mentioned, sometimes we don't remove space per se, so we can't rely on space or like a new line.
This is an artifact of the tokenization. Don't worry about it.
Thank you very much.
Okay, you're welcome. Any other questions?
Yes,
Yeah,
Doctor.
Doctor, I may just add something or just confirm it. Can I add? Can I talk?
Yes, sure.
So, Doctor, just confirming that when we make during the self-attention, as if we represent each word using the context in which it's mentioned, but we not in the training example or in the self-attention we add, for example, 8 to animal. No.
No. We don't do that manually. Yeah, we leave the machine learns it by itself by going through so many examples.
So yes, so the goal of the self-attention is to represent each word, giving the context. It was mentioned.
Yes.
That's it.
And thank you. And it is important also to understand that this is bidirectional. And it doesn't depend only on the previous words, because as you saw, all the input is all at the same time given to the transformer. Okay, it's not just the first words. Okay, all of them. So the attention is done on the entire sentence, not the words before or the words after. Okay, and thank you, Marwa, for raising this point, that this is like understanding the context of the sentence. Exactly. I think Watak, you had a question? Or someone else?
Doctor Bashir.
Bashir,
Yeah, Doctor. Yes. But why I need the multiple layers of encoder instead of using one encoder, and will learn the relationship between words, and they give us another meaningful words.
Very good question. Okay, each layer, if you this is one of the concepts of deep learning. Each layer learns a specific concept, and as we go deeper in the network, it learns higher level concepts. Okay, so the typical example is always like in images. The lowest layer learns something about points and edges, and then the layers above learns about shapes, and then the layers above learns about objects. Okay, and so on. So as you move up in the architecture, if we're assuming that the input is from the bottom, if you move up into the deep network, you learn higher level concepts. Okay, so we expect here by self-attention at several layers that we learn different representations of the words that capture different contexts. Maybe some of them will capture the notion of the part of speech tagging, which is which ones are nouns and which ones are verbs, and so on. Okay, maybe at one layer we can learn entities, that the street is an entity by itself, and the animal is an entity. Okay, and so on. So different layers of understanding. Okay, starting from the sentence and then moving up, you learn higher level concepts. Did I answer your question, Bashir?
Doctor, thank you.
Okay. Any other questions? Okay, so let's move on. So we mentioned that self-attention is the mechanism that the transformer uses to bake, to involve, or to consider understanding of other relevant words into the one that we are currently processing. And remember that we are processing all the words simultaneously. Okay, so now we are actually learning signals or attention signals between every word with the other words in the sentence. Okay. This idea was extended by using what we call multi-headed attention. So we can have multiple attention, we don't call it attention layers, but we call it attention headers. Okay. Each attention header, or each, you can think of it as a vector of weights, is initialized in randomly and learned together, and maybe each one will learn something different. Okay, so for example here, this is another head of attention. So all of these are done in parallel. Okay, so at each layer we have multi-headed attention. We learn, or the network learn, multiple attention weights at the same time for the same sentence. Okay, so this is another head of attention that relates it to tired. So you see here the weight to tired, which is 2, by the way. Okay, so one head attained the animal to it, and another attained more tired to it. Okay, so that will allow us to not us, of course, allow the machine to learn encodings in different spaces, in different embedding spaces. Okay, so actually each of these will provide a type, or not a type, different embeddings, and these embeddings are combined together before going to the next layer. Okay, so that's another dimension, another extension of learning concepts, or learning the context within each sentence. So we learn it in different ways. Okay, it's like giving this sentence to multiple people, and each one will learn something about that sentence. Okay, initialized randomly, and then we will combine all of these embeddings before going to the next layer. So that's another concept. So the self-attention concept is learning some attention weights between within the sentence. We can repeat that. Okay, starting from different initialized weights, learning different attention weights in parallel, and these will be combined before going to the next layer. Okay, is that clear? Any question about this? Okay, good. I don't know if you hear me or not. Any indication that you hear and see me and the slides?
Yeah, we hear you, Doctor.
Yes, Doctor. We all
Okay.
can hear.
Okay, very good. Okay. Sometimes when I don't get any questions, I worry that I'm talking to myself. Okay, so just bear with me. Okay, another concept that we will go through quickly, which is also important in transformer, is positional encoding. Now, we said that all the words will be given simultaneously to the transformer. Now, how can the transformer understand that this word appears before that word, and that word appears before that word, and so on? There's no notion of any order. Okay, so this is like bag of words. We gave all the words at the same time to the transformer. So there must be a way to distinguish the positions of the words. Okay, so this is what we call positional encoding. It is done in a special way using sine and cosine functions. We don't care about exact mathematical notion here, but it is important just to understand that positional encoding here is added or summed to the initial embeddings before that embeddings go to the first encoder. Okay, and this is only because we want to distinguish between the positions, because that's important, right? In understanding the language, it is important to understand which words appear in which position, because that will affect the structure of the sentence. Okay, so now we extend or relax our definition of the input a bit. Earlier, we said that the input is words. Of course, words cannot be just input to the network. We have to represent them using embeddings. And then now we are saying that it's not just the embeddings, it is the embeddings plus the positional encoding, which now combined together will be the input, the actual input to the first encoder. So that's another concept of the transformers, and that's representing the order of the sequence. There are more details, of course, in the encoders that we don't have to talk about. But as you see here, there is something called add and normalize. It's another layer for normalization after self-attention, which is repeated. Let me change this. Which is repeated in the self-attention sublayer and also in the feed-forward sublayer. But don't worry about that. It's just, you can think of it as the self-attention and the feed-forward network. Okay, and of course the stack, whatever the output of that encoder will be the input to the next one. Okay. Type. Now let's talk about the decoder. The decoder, as we said, is very similar to the encoder, except that we have 3 sublayers instead of 2. So in the decoder, we have the self-attention and the feed-forward network, and that's repeated over the stack. In the decoder, we have self-attention, then encoder-decoder attention, then the feed-forward. Okay, type. Now let's now I think the right time is to talk about what we mean by encoder-decoder attention. I hope you understand what we mean by self-attention, right? That's capturing the relationships between the words in what? In the input sequence. Okay? That self-attention is doing the same thing, but for the output sequence. So here, as you will see in the next 2 slides, we will start to produce the output sentence, okay, one by one. We need also to understand relationships between the words in the output sequence, and that's the role of the self-attention layer. It's very similar to the role of the self-attention layer here, or sublayer here in the encoder. Now we extend this idea to get relationships between the words in the input sequence and the words of the output sequence. And that's what we call encoder-decoder attention. And you will see here that input to that sublayer is from, of course, the previous sublayer, which is the self-attention layer, and also the output from the decoder stack, which is the attention, which represents the attention, the self-attention within the input sequence. So the role of, or the job of this sublayer, the encoder-decoder attention, is very similar to self-attention, but instead of looking only into the output sequence or the input sequence, it looks at both. So this one is the most important one in our example, the machine translation, that will relate the word student to, I don't know, étudiant, okay, the translation, or the vice versa, étudiant to student. That will relate, that will learn that these words are actually related. Okay, so that's the role of the attention at the decoder level. So we have actually 2 sublayers of attention. One, self-attention, which is the self-attention within the output sequence, and the other is capturing both the attention between the attention within both the input, or between actually the input and the output sequence, which is important generally in any sequence-to-sequence task, because sequence-to-sequence means that you will be given a sequence and you want to produce an output sequence. Okay, so there must be a relation somehow between these two, and that's captured to the most extent by this sublayer. Okay. Right. Let's see these animations, these nice animations that shows us how the decoder works. So decoder works at time steps. Okay, so at that slide you will see the first time step, and then in the next slide you will see the next time steps. In the beginning, in the first time step of the decoder, we don't have any input here, so we'll input everything to the encoder, and we get the final embeddings, like what you see here. These are, you can think of them as the attention weights, okay? And these attention weights are input to all the encoders here. So this is attention weights that we learn at the last encoder, okay? Now this is given to each encoder. Now you will see that the decoder, the stack of decoders will provide the first word in the output. Remember that we are at time step 1. So at time step 1, we assume that we are done with all encoding step. So the input sequence is given to the encoder stack, and now we have the output of the encoder stack, which are the embeddings, the blue ones here, and the attention vectors, attention weights, or attention matrices. These matrices are given at time step 1 to provide the, and of course every time, but we are looking at time step 1 now. It is given at time step 1 to provide the first output, which will be a word, as you will see here, I. Okay, je suis étudiant, so I am a student, so I is the first word. Okay, so understand now this animation. We'll talk about this linear and softmax layer later, but let's assume that the decoder stack will provide the output. Now, how do we know that the output is I? The network doesn't understand the words, it understands numbers, right? So the output here will also be an one hot encoding that tells us which word. So if we have the vocabulary of our collection, let's say that we have 10,000 token or words, okay? So the output will be a vector of 10,000 values, and it will be like a probability, okay? I think we will see that, I think, in the next slide. It will be like a probability for each word. So let me do it quickly here. So it's like a very long vector from 1 to 1,000, assuming that we have only 1,000 terms. Each one here will be a probability. So let's say that this is the maximum probability. Let's say that this is 0.8 probability. Okay, so that's the maximum. So this corresponds to, let's say, 8,512. The word number 8,512. Okay, this corresponds to, let's say, the word I. If that's what the network learned, then this is correct. Okay, if not, then we will indicate that this is an error, and that's how the network will learn next time to produce I. Okay, so now after the first time step, we got I here, which is the first word. Before we continue, any question on this?
Doctor?
Yes.
You said that all the words will go simultaneously, so I expect that all the words will output simultaneously.
No,
understood.
No, this is not how the decoder works, okay? So the encoder gets all of them simultaneously, but then the decoder will produce one word at a time, okay, in sequence. Okay, is that clear now?
Yes.
Okay, any other questions? Okay, good. Then let's see the next animation. Now we assume that we have I, We are at step number 2. You will see that we get am now. Okay, then I think we need to stop this at some point. Okay, so let's first see the animation. I will give you like a minute or so to see the entire animation, and then we will explain it. So it starts now. So you will see that the decoder stack gets one new input, produce an output. Okay, and you'll see that this input is the previous words that were already provided as an output. Okay, so at the beginning, the first one was I, so I will be input here to produce the next one, which is am. Then you will see am here, which will go to through the decoder stack to produce A. Then I am A will go to the decoder and produce student, and so on. Okay, so every K words in the beginning, if you see the output, will go as input to produce the K+1 new output term.
So, Doctor, in step
Yes,
number
please.
1, the input will be the embeddings from the encoder, but step number 2.
Yeah, because in step number 1, we didn't have any output yet. So there is no input to the decoder except the attention weights here.
Okay, starting from step 2 will be the output, will be the input and...
Yes, exactly. So this I, assuming that this I now is the first output, will go and will be the input, the only input to the decoder stack. Because now that indicates that give me the next word after I. Okay, so I, after getting the word I from the output, it will be input back to the decoder stack to produce the next one. So the next one will be am. Now am will be next here, and now the new input to the decoder stack will be I am, and I will in that case it will be produce A. Then A will be in the input here.
Doctor?
Okay, and so on. Yes.
Yeah, just
yes,
sorry for the silly question. I just need to clarify. Like, so the decoder usually have 2 inputs: the actual input from the language translation, like for example this French sentence. We take it word by word, and then
the previous translation, the previous output so far.
So like we don't take in mind what's the original input was, like for example, like in this, because in this example we have the
No, we have, of course we have.
Yeah.
We have, because we have this output, right?
Yeah.
This output goes into all the decoder stack. Okay, so this is what we learned from the encoder stack.
Okay.
So this is like we did encoding. Now this encoding is input to the decoder stack, plus what we have provided so far as an output.
So the first input, that means it's just the empty sentence, like nothing, and then
exactly
the first output is I.
Yes.
All right. Thank you for clarifying.
You're welcome. So let me show you now the next animation, which is the next time steps. Okay, so I am, then you'll see I am here, then A, you'll see A here, then A will be the next input here. It's not A only, but I am A, then student will be provided, then student will be input with the others to provide actually end of sentence. End of sentence indicates the end of the output. Okay, so of course, this is like when we use the, just one second, it's like when we use the transformer, but in training, every output here will check if it is correct or not. If it's not correct, then this is a negative example for the model, and the model has to change the learned weights so that this will not happen next time. Yes, questions? Someone was asking?
Doctor, just to clarify one point, do you mean that the attention weight, you call it the attention weight, it will be an
the attention
input
matrix here, yeah. This one?
Yes. it will be input to decoder only in the first step. Then the
No, I didn't say that. You see it here.
Yes.
This is all that comes. This is always input.
Yeah, okay. It's always input with the output from the.
So far.
Yeah, okay. Yes.
Yes.
Okay,
Yes.
thank you.
Yes. So at time step 1, the input is the attention. So let me write here the input. So the input for this is the attention only. And I liked what Muhammad said, empty string, okay? Nothing, we don't have anything yet. Then here will be the attention also, plus I. Then here will be the attention also, plus I am. Then here will be the attention also, plus I am A, and so on. Okay, I hope that this is now very clear. Any other questions?
Yeah, sorry to drag this too long, but
No problem, Muhammad.
the KMV are weights, not actual inputs. They're actually going to be the weights that are used to find.
Yes, you can think of it as what the network learned from the input sequence. It's like an encoded version of the input sequence.
All right, thank you for that.
Okay. You're welcome. Any other questions? Ask me, please, because this is a very important point to understand how the decoder actually works. Of course, we omit lots of details. You can read the paper if you want to get the details, but this is the very high level gist of it. Any other questions? By the way, all of these nice figures and animations came from a blog that I gave you the link to by Jihad Al-Ammar. Actually, very informative blog post, mashallah, trying to explain how the transformer actually works. So there are more details, of course, especially about the self-attention and the positional embeddings that you can find there. Any more questions, or we should move on here?
Doctor, what will happen with the second sentence? Like this K and V matrix will be like improved with second or third sentence, or we will
it will okay, good. It will improve in the training phase. Okay, but by the way, this is not static. This is static for this is the output for this given sentence. These matrices will be different for different sentences, of course. Okay, and these matrices are output of that learned model. So this learned model, if we made any mistakes in training in the translation, of course, this will be improved or further trained, and this will be further trained. Okay, is that clear, Hira?
Yes, doctor. And doctor, one more question. You said that the input to this attention layer will be dependent on each other, right? Like X1 and X2. And then they will become
at each layer, by the way, at each layer.
Yeah, that's
because
what I'm asking.
The input changes over layers, of course. Yani X1 and X2 here means the input to that layer.
But they will become independent after becoming the output, right? So when they will go to the second attention layer, will they be independent or dependent?
Each self-attention layer works over all words, Hira.
Okay, I got it now. Okay, thank you, doctor.
You're welcome. Okay, I think I need to move on now. So here we will just explain the part that is at the end of the stack of the decoders. At the end, we will get the output, which will go to so that's the embeddings at the last layer of the decoders. Will go to a linear layer, and then from this linear layer, you can think of it as like a weighted average. for each of these numbers, we'll get an output which will be at the vocabulary size, as I think I explained here. So that's the vocabulary size here. Okay, so if the vocab size is 1000, then we'll get 1000 numbers out of this. And then just to convert these numbers, so these numbers can be positive, can be negative, then it will be converted into probabilities using what we call softmax layer. Okay, so that softmax layer will just convert these numbers into probabilities. Okay, so now this is a probability distribution. I can look at which one has the higher probability and look it up in my one hot mapping to see which word is that corresponding to 5, which happened here to be M. Okay, so we get just the index of that highest value, and we'll now assume that this is now the output word of that of the decoder stack at that step. Okay, so that's any more explanation about the output. All of that is above what? Above the decoders. So that's the decoder stack here. Okay, at the end of the decoder stack there is embeddings. That's the output of the decoders. Okay, and that goes into the linear layer, which is like one layer of a neural network, and then goes to the softmax just to compute to produce probabilities, which will correspond to the word that we will consider that this is now the output of the network. Okay, so this is just repeating what I mentioned earlier. This is overall.
You said something.
Yes.
That's the machine will know that there is something wrong and will learn from this mistake or whatever.
Yes.
How is that? How she will know that there is a wrong or mistake in this point?
Okay, let's say that instead of am here, let's say that 5 was not am, it was. The word was. Okay, this is wrong, right? Because it's a present tense in French, so it has to be present tense also in English, right? So in training, if that 5 corresponds to was, we know that it is wrong because in training we have it's supervised. So we have for each for each French sentence, we have the correct English sentence. So we know that was is wrong. Okay, so we know it in training. Of course, in actual using, in inference, when we want to use the trained model, we will not know. Okay, but in training, that's how we train the model. We train the model based on labeled pairs. Okay, so we know that was is wrong. Then we by back propagation we update the model. Okay. But once training is done, خلاص, we will not know. So what happens in inference at real time is that we will see what is that number, and that number will give us was. خلاص, was is the translation, then was will be input for the input here for the next time step. We will not know, of course. Okay, we'll just get whatever the network will provide for us. But in training, we know. Did I answer your question, Marina?
Yes, thank you, Doctor.
Okay. Any other questions? No questions? Okay. Sometimes that's good and sometimes it's not good. I assume that it's good. Anyway, the transformer architecture was shown to be very effective in many natural language processing tasks. This is the architecture as it is shown in the paper. The paper, by the way, is called, it is really nicely titled, "Attention is all you need." Okay, and of course they mean that the concept of attention is really was the key concept to learn in such architecture. So that's what you see in the paper, and it's a really famous figure to remember always.